In this video, I'm going to run through the AQA Physics GCSE Unit 2A pre-exam. The first part of Unit 2 looks at force and motion, and the three principles underpinning forces are Newton's laws of motion. Newton's first law states that an object will remain at rest, which basically means it's stationary or not moving, or at a constant velocity unless an external force acts upon it. This means if an object is stationary, it will remain stationary until an external force acts on it, or if an object is moving at constant speed, it will remain at constant speed until an external force acts upon it. Newton's second law is basically an equation which states that force equals to mass times acceleration. You've got it broken down for you here, which is F equals m times a, and you've got the idea that force is measured in newtons, mass is measured in kilograms, and acceleration is measured in meters per second squared. Newton's third law states that every action force produces a reaction force that is equal in size but opposite in direction to the action force that created it. So you take the example I was drawn at the bottom there. If a person pushes onto a wall with a force of 20 newtons, that being the action force, then the wall must push back on the person with the same size force but in the opposite direction. So the force will have a magnitude of 20 newtons but it will be acting in the opposite direction. If you look at the block above that I've just drawn here, you can see that it's got 5 newtons acting to the left and 10 newtons acting to the right. That means that force will experience an acceleration because the resultant force acting on that object will be at 5 newtons this way, and therefore the block will accelerate to the right. At the end of the last slide, we looked at resultant forces. A resultant force is the overall force acting on an object. So you can see here that we've got a vehicle going forwards. It's got 100 newtons acting to the front, and then it's got 25 newtons worth of air resistance, 10 newtons of friction on those sets of tyres, and 10 newtons of friction on those sets of tyres. So to work out the resultant force, we would do 100 minus 25, add 10, add 10. That will give us an overall resultant force acting in the forwards direction of 55 newtons. If you do have a resultant force and you're already moving, the object will speed up, slow down, or change direction. So in this case here, the car is actually accelerating forwards. If the car was stationary to begin with, then the object will begin to move if there's a resultant force acting on it. If you've no resultant force acting and you're already moving, then you'll continue to move at constant velocity until you end up with a resultant force acting on you. And also if you were stationary to begin with and there was no resultant force acting on you, then you'll remain stationary until a resultant force begins to act. So we've mentioned acceleration briefly on the previous two slides. Acceleration is a change in velocity over the time taken for that change. And that can be written as a equals v minus u over t, where v is the final velocity and u is the initial velocity. When we represent motion, it's always useful to represent that as a graph so we can work things out from the graph and the graphical display we have there. So the first types of graphs we're going to look at are distance time graphs. Now we can see here that we've got a various range of different time graphs. The thing to remember with all distance time graphs is that the gradient indicates velocity. Okay. Now the first graph that we'll look at is one that's speeding up, so you can see that we've got a curve upwards. That means that the object is beginning to travel a greater distance in the same amount of time, so it's actually accelerating. With this one, there's no change in distance with time, which means that the object is stationary. This graph here, we have a constant gradient, so that basically means that there's always the same change in distance over the same time period, so that means that we're moving at constant speed or constant velocity. And in this case, the distance we travel is decreasing in the same time period as we go up, so that object there is slowing down. If we just look at the graph that I've got here, if we imagine that these lines are straight, if you were asked to determine which of those lines, the blue, the red or the black line, was the fastest, then remember that the gradient is equivalent to velocity, as we've already mentioned, which means that the fastest line is one that travels the greatest distance in the same amount of time, so clearly the blue line is the fastest, so I'll just put an F next to that one, and the black line will be the slowest, so I'll put an S next to that one, and obviously the red line would be somewhere in the middle. We can also display data as velocity time graphs, and velocity time graphs obviously showing us something slightly different to distance time graphs. If we look at the ones that we've got displayed on the side here, a straight line this time means that an object is travelling at that velocity for that time period. So that's constant speed going in the forwards direction because it's a positive on the graph. If we look at the next one, we've got a stationary object. For something to be stationary, it would have zero velocity, it's not moving, so the velocity there would be zero, which is why it's straight down the axis. If we look along here, we start off at a velocity, a value, and we decrease to zero, so that's clearly slowing down, so it's a straight line. We then have another one with a straight line going upwards, so that's obviously speeding up. And the final graph we'll look at is the idea that we can have negative numbers on velocity time graphs, and that indicates the direction they're travelling in. So this object here has got a constant velocity, but it's in the negative direction, so that would mean that it's travelling backwards relative to the observer. The thing to bear in mind is that the gradient is the acceleration for velocity time graph, and the area under the graph is equal to the distance. On this slide, we're going to look at a question about velocity time graphs. This question asks us to find the total distance travelled by the vehicle. So to do this, we need to remember that the distance is equal to the area under the graph. The next step is to work out the area under the graph. To do that, we'll need to break the graph down into different sections. So I'm just going to put some lines on it now to show you the sections that I'm going to use. So I'm going to break a triangle off there. Let's turn that into a rectangle. And we've got a triangle here. And a triangle there. So we're going to have area 1, 2, 3, 4, 5, 6. And to work out the total area, we'll find the areas of those different parts and add them all together. To find the area of part 1, we realise that part 1 is a triangle, and we need to use then that part 1 will equal a half times, for a triangle it's half times base times height, so for area of a triangle it's half times base times height. Our base here is 10, and we're going to times that by the height, which goes from 0 to 20, which will be 20. That leaves us with an answer of 100. So part 1 we get an answer of 100 metres. For part 2 we're looking at a rectangle, so we're going to do base times height for that one, and we can see that the base runs between 30 and 70, so that's a distance of 40. I'm going to multiply that one by the height, which is 20, and that will give us an answer of 800 metres. So you can write 2 up here, 800 metres. Part 3 now, we're going to use the same thing as a triangle, so it's going to be half times the base of that, you can see is between 50 and 40, which gives us 10, multiplied by the height, which is 20 and 30, which also gives us 10. Put that into our calculator, we get an answer of 50. So 3 is 50. Looking at 4 now, again we're going to do base times height. We can see that the distance at the bottom there is between 60 and 50, which gives us a distance of 10, and the height is between 20 and 30, which is also 10, so that'll give us 10 times 10, which equals 100. So 4 will be 100 metres. So part 5 we will know is already 50 metres because it's the same triangle that we did with as number 3, so that's going to be 50 metres there. If we did that, so we do a half times 10 times 10, so 5 we should get 50 metres out as well. And 6 is going to be our final one now when we look at 6. So here we can see we've got a distance between 70 and 90 is 20. That goes up 20, so it's a half times 20 times 20. And that gives us an answer of 200 metres. So to find the overall distance travelled, what we need to do is we need to add all these areas together, and that will give us our overall distance. So we're going to add 100 plus 800 plus 50 plus 100 plus 50 plus 200, and that gives us our overall answer. And once we've added all those together, we get our total distance being equal to 1,300 metres. So we're going to look at another question 2 velocity time graphs now. It asks us to find the acceleration. Now remember that for velocity time graphs, the acceleration is equal to the gradient So A equals gradient. And the gradient is equal to change in y, delta y, divided by the change in x. The first part I would like us to do that calculation is between 20 and 30 seconds. So looking here, you can see 20 and 30 there. So we wanted to know the change in y by change in x at that point. So we can see that y has changed by 20 meters per second, and that what we've got here is our x has changed by 10. That's 30 minus 20 to get 10. And so therefore our acceleration at this point will be 20 over 10, which gives us 2. The units for acceleration, remember, meters per second squared. The next question is asking us to do this same process between 40 and 50 this time, so 40 and 50. So that's this bit here. So we can see that the change in y is going to be 10. I've put that by doing 30 minus 20 to get 10. And the change at the bottom will also be 10. It's a shallower gradient, which makes sense. And so in this case, A will equal 10 over 10, which will give us 1 meter per second squared. The final one we're going to look at is between 60 and 90, so 60 and 90 takes place here. So this is this point. If we look at the change that takes place in the y direction, well, it's gone, starts at 30 and ends up at 0, so that's a change of minus 30. And that takes place over 90 minus 60, which also gives us 30. So our acceleration is equal to minus 30 over 30, which will give us minus 1. So it's equal to minus 1 meters per second squared. And the way that we've calculated the gradients there to find the acceleration, remember that if this was a distance time graph instead, then we'll be able to work out velocity by doing the gradient calculation in the same way that I've shown you here. So now I'm going to look at stopping distance. Remember that stopping distance is the overall distance travelled when a car or vehicle is trying to stop, and that's broken down into 2 separate distances. The first of these is called the thinking distance. Remember that the thinking distance is the distance travelled and the time it takes a driver to realise they need to stop and press the brakes. So it's from them seeing the initial hazard, the distance they travel from seeing the initial hazard to eventually pressing the brakes. Obviously once the brakes are started, then we will stop looking at thinking distance and move into braking distance. And braking distance is the distance travelled after the brakes have been applied until the vehicle stops. Just a reminder about the energy transfers that take place here, which is basically that when the brakes are applied, work is done by the frictional forces between the brakes and the wheel, and that reduces kinetic energy of the vehicle, and the temperature of the brakes increases. So if you're asked to explain what energy transfers take place, that's your definition there. The idea that work is done by the frictional forces, and that changes the kinetic energy of the vehicle, and the energy transfer that takes place is from kinetic to thermal energy that heats up the braking system. So we're going to look at factors that increase stopping distance. Remember that stopping distance is broken down into 2 areas, thinking distance and braking distance. The first one we'll look at are factors that affect thinking distance. So the first one is that the greater the speed of the car, the greater the velocity of the car, the greater the distance you'll travel at the time it takes you to realise you need to start pressing the brakes from seeing the hazard. So the greater velocity increases thinking distance and therefore increases stopping distance. Other factors that affect thinking distance are also things like distractions. So if you're on your mobile phone or you're talking to someone on a hands-free set in the car, you might not be giving the road your full attention, and therefore your thinking distance will also increase. If you're tired, then again you tend to react more slowly, and therefore in the extended time it takes you to react, the vehicle will have travelled a greater distance during your thinking time. And finally, the last one is alcohol or drugs. So if you're under the influence of alcohol or drugs, your reactions are again slower, which means that the vehicle will travel a greater distance before you realise you need to press the brakes. We move on to look at factors affecting braking distance now. So again, the same with a greater velocity. If you're travelling at a greater velocity, the brakes need to do more work, more energy needs to be transferred away from the car to reduce your kinetic energy. Therefore, it takes you a greater distance to stop. If the road conditions are wet or icy, again there's not as much friction between the tyres of the car and the surface of the road, so your braking distance will increase. If you've got bald tyres or lack of tread on your tyres, again the distance will increase because there's not as much friction. If you've got warm brakes in your vehicle, again the braking distance will increase because there's not as much friction. And finally, the last one is that the more passengers you have in the vehicle, the heavier the vehicle is, therefore a greater force is required to stop the vehicle, which increases the braking distance. So we're going to move on to look at terminal velocity. To understand terminal velocity, we need to understand forces. Your exam board, AQA, do this in the context of a skydiver. So the start of the jump, the air resistance is small acting on the skydiver. So if you imagine you just jumped out of the plane, the only force acting on you is your weight, and that will cause you to accelerate downwards. As soon as you jump, you're not actually moving through the air at first, if you take a snapshot there, so there's no air resistance acting on you. But as soon as you begin to fall, you will collide with air particles in the air that you're falling through. Those air particles will strike you and produce a force acting upwards, and that's known as air resistance. So as you begin to fall, your air resistance begins to increase. As your speed increases, air resistance will increase as more air particles collide with you in a given time. You'll continue to fall and you'll pick up speed until eventually air resistance will be large enough to balance the skydiver's weight. At that point, the forces are balanced and we're said to be travelling at a terminal velocity. As you can imagine, that velocity is quite high, so to make sure we land safely if we're doing a parachute jump, we would then open our parachute. And if you want to find out what happens there, you just move on to the next slide. So when the parachute is opened, the parachute has a large surface area, so that increases air resistance. So when you open your parachute, or in this case when the skydiver opens his parachute, air resistance suddenly increases, and that causes the skydiver to slow down. Because if you imagine at this point, your resultant force acting upwards, therefore you're decelerating. As you begin to slow down, then you're going to have less particles colliding with your parachute and yourself in a given amount of time, and therefore air resistance is decreasing. So air resistance will continue to decrease until it balances your weight again, and at that point the skydiver now has a new lower terminal velocity. So if we see this point here, when they're both balanced, when both forces are balanced, that's when he's travelling at his new terminal velocity. So if we look at a velocity time graph for the skydiver's journey, you can see as soon as you jump out of the plane, you've only got weight acting on you, so you begin to accelerate. That rate of acceleration is decreasing, so we get a curve here, because air resistance is increasing until you reach your terminal velocity. You can see you're travelling at a terminal velocity here. At this point, the skydiver opens his parachute, and we see a sudden decrease in velocity until we reach a new terminal velocity here. And you must remember that terminal velocity occurs when there is no resultant force, and that occurs when weight and air resistance are balanced or are equal to one another. So just very briefly going to look at Hooke's law. So force applied to an object can cause an object to change its shape. Remember that elastic potential energy is the energy stored in a system when work is done to change its shape, so long as the system can return to its original shape again. That's elastic potential energy. So when we add masses to a spring, we are storing elastic potential energy, and we cause the spring to stretch. Hooke's law states that the force is equal to the spring constant multiplied by the extension, where the extension is the extended length minus the original length. And you need to know about the units. So force is measured in newtons, extension is measured in meters, which means that the spring constant will be measured in newtons per meter. So we're going to look at the difference between weight and mass here. So on Earth, you need to know that the gravitational field strength is 10 newtons per kilogram. That's not given to you in the exam. You need to know that and take that information in with you. It's actually slightly lower, but for GCSE you need to know it's 10 newtons per kilogram. Okay. In other words, that means that a 1 kilogram mass is pulled downwards by a force of 10 newtons. And therefore we can calculate weight on Earth by doing weight is equal to mass times gravitational field strength. Remember that when we measure mass, it should be in kilograms. Gravitational field strength is measured in newtons per kilograms, which gives us our weight in newtons. So you need to remember that weight is actually a force and is not measured in kilograms or stones. If someone's telling you that they weigh 60 kilograms, then they're wrong. Their mass is 60 kilograms, and their weight, at GCSE at least, will be 10 times 60 to give you 600 newtons. Remember that that equation is basically that a force is mass times a acceleration, where gravitational field strength is actually the acceleration that a falling object falls at if they fall on Earth. So remember that the acceleration that someone skydiving would fall at is 10 meters per second squared. And just a reminder that force is equal to mass times acceleration. We're going to briefly look at work done now. So when any object is moved around, work will need to be done on it to get it to move. And we can work out the amount of work done in moving an object using the formula shown below. So work done is equal to force times distance moved. Work done, remember, is measured in joules. It's an energy transfer, remember. Force is measured in newtons and distance is measured in meters. When work is done to a system, the system gains energy, so energy is transferred to that system. And when work is done by a system, the system will lose energy, and that energy is transferred away from that system. Looking at two more types of energy, so remember that work done is force times distance moved. We can also express work done in terms of energy. We've got two energies that you need to know about for this exam. They're kinetic energy and gravitational potential energy. So any object that moves will have kinetic energy. The amount of kinetic energy an object has can be found using the equation, which is one of the hardest ones you need to learn, which is kinetic energy is half times mass times velocity squared. So K equals a half mv squared. Where kinetic energy is an energy, so it's measured in joules, the mass is measured in kilograms, and the velocity is measured in meters per second. Gravitational potential energy is the energy that an object will have if it's raised above the ground. So any object that has a height will have a gravitational potential energy. The amount of gravitational potential energy an object has can be found using the equation shown below, which is Gp equals mass times gravitational field strength times height. So Gp equals m times g times h. Should be a times there. And G, remember, is 10 newtons per kilogram. The key, really important thing about both of these things is the kinetic energy that an object has at the bottom of a fall is equal to the gravitational potential energy the object had at the top before it began to fall. And therefore, if you know how high an object is at the start, you can work out its kinetic energy at the bottom, because you can work out the GP first. That's equal to KE at the bottom, and therefore from there you can work out the speed that the object will be travelling at when it reaches the bottom. Momentum's another physical quantity that you need to be aware of. Any object that moves has momentum. So if you've got mass and velocity, that's your momentum. Momentum equals mass times velocity. Mass, remember, is measured in kilograms. Velocity is measured in meters per second. So if you times those two things together, you get the units for momentum, which is measured in kilograms meters per second. The only reason we're really studying momentum is because of this bit here, which is the idea that momentum is conserved. So in any collision or explosion, the momentum before is equal to the momentum afterwards, provided there are no external forces acting on that system. That's really useful. So if you're given a situation, you might be given like a collision, and you might be told some conditions beforehand, you know that the total momentum of the system before is equal to the total momentum of the system afterwards, and that allows you to do calculations and work things out. Momentum is also useful in understanding how we reduce the impact of a collision for things in vehicles such as airbags, crumple zones or seat belts. Now there's two ways to explain these. The first one is explaining it using work done, and the second way of explaining it is using momentum. Now, for your exam, you don't have to learn the equation, or you're not given the equation that force is equal to change in momentum over time, which is why we're going to explain it using two methods, because you are given the equation that work done is force times distance, or in this case, force equal to work done divided by distance. So I'll talk you through how to answer a question if it comes up, such as how do seat belts or crumple zones or airbags reduce the impact of a collision or the force acting on a person. So the first thing to realise in both arguments is that the force is the thing that causes injury. And the idea of using seatbelts, crumple zones or airbags is to try and reduce the force acting on the person who's involved in that collision. So if we look at the work done method first, for all collisions the work done to stop the object is the same. So the same energy transfer. You'll be travelling at a certain speed, that'll give you kinetic energy. In a collision, that kinetic energy is going to be all dissipated away and turn into other forms of energy. So kinetic energy is going to change to zero. So your work done, your change in energy, is the same. So therefore, all safety features, be that airbags, crumple zones, or seatbelts, are designed to increase the distance of the impact. So the seatbelt will stretch, increasing the distance. The airbag obviously inflates and then deflates, increasing the distance. And the crumple zones will crumple together, increasing the distance of the collision. So if we increase the distance for the same work done, you can see that the force is going to decrease. To increase distance, decrease the force, and by decreasing the force, that makes injury less likely. So now we'll try and discuss this in terms of momentum. Remember that the equation for momentum is that force equals change in momentum over time. You're not given this in the exam, so you need to learn it going into the exam if you want to explain this question in this way. So first thing you need to know is that for all collisions, the change in momentum is the same. So you will have been going, at the beginning your momentum will be mass, the mass of the vehicle multiplied by the velocity it's travelling at. At the end of the collision, your momentum will be zero because you're no longer travelling, so your velocity will be zero, therefore making momentum zero. So in this case, all safety features increase the time period of the impact. So things like the seat belts will stretch, making the collision last longer. The airbag will, deflate, making the collision last longer. And the crumple zones obviously will compress, making the collision last longer. So time is increased, and you can see that for the same change in momentum, an increase in time will decrease the force, and again, once more, decreasing the force makes injury less likely. Let's look at static electricity now. So we've got this straight from the specification. When certain insulating materials are rubbed against each other, they become electrically charged. Negatively charged electrons are rubbed off one material and onto the other. So if we take, for example, what we've got here, so if we move the cloth backwards and forwards along the rod, what will happen is electrons from the rod will move to the cloth. Remember that electrons are much, much smaller than the nucleus of the atom, and therefore it's the electrons that do the moving. So when we rub the cloth across the rod, electrons from the rod move onto the cloth. Because you gain more electrons and electrons are negatively charged, the cloth becomes negative in terms of its charge, and because the negatives are moved away from that rod, the rod is then going to become positive. So let's explain why the material that gains electrons becomes negatively charged, and the material that loses electrons is left with an equally positive charge. When two electrically charged objects are brought together, they exert force on each other. Now the thing that you need to know is that if we bring two objects together with the same charge, which is two negatives, well they're going to repel because they've got the same charges repel, and they're going to push apart from each other. If we bring two objects together, they've got opposite charges. Remember that opposites attract. So two objects that carry different types of charge attract each other and they will move together. The other thing you need to know about electrical charges is that they can move easily through some substances, for example metals, and those materials are called conductors. So if electricity can move through an object, it's called a conductor. The things we've got here for static electricity usually involve insulators, because once the charge has moved onto one of them, it doesn't move away, which is why this effect is not observed with metals. So some key definitions for electricity now. The first one is that current is a rate of flow of charge. Remember that current has a symbol I, okay, and that we can use the equation here that charge is equal to current multiplied by time. So current is a charge that's stored on an object or passes through an object in a given time. And that's measured in amps, which has the symbol A. The next one we're going to look at is potential difference. Potential difference is the energy per unit charge. So that's the amount of energy each electron carries. That's measured in volts, and the potential difference can be calculated by doing the energy transferred divided by the charge. And that's given by the equation that's shown here. Energy transfer equals charge times voltage. If you're asked to define either current or potential difference in the exam, remember you can just use the equation for those things which you can find on the formula sheet. And remember that current is charge per unit time, and the potential difference, also known as voltage, is the energy transferred per unit charge. Voltage and current can both be related using Ohm's law. which is that the voltage equals current times resistance. So remember that the potential difference is proportional to your current, and resistance is anything that reduces an electric current, and that's measured in ohms and has the symbol omega. You also need to be aware of standard circuit symbols, and also what those circuit symbols represent and what those devices do. So you should know that an open switch means that the circuit is broken and no electric current is flowing around. If you close a switch, you will then get electric current to flow around the circuit, and therefore electrical energy will be transferred. A cell is what provides energy for the circuit, and that's a single cell. Multiple cells, so 2 or more cells, gives you a battery, and a battery also provides energy for a circuit. But if you draw one cell, remember you must call it a cell, whereas if you draw 2 or more, that's a battery. So in the exam, if it asks you for a battery, to draw a battery, you need to draw 2 or more cells. The next circuit symbol we'll look at is a diode. Diode only allows the current to flow in one direction. So this diode here will only allow current to flow in this direction. Current cannot flow to the left, it can only flow to the right, because you've got a very high resistance in the opposite direction. The one below is a resistor. This circuit symbol here is a resistor. There are quite a few different types of resistors, and they've all resistors have the square or rectangular box with no line going through it. The one below this resistor is a variable resistor. A variable resistor, you can change the resistance of that resistor, so you can make the resistance more or less. Whereas a fixed resistor, which we've got here, that resistance can't change, it's set at a predetermined value. This circuit symbol shows a lamp. Remember that a lamp will glow when electric current passes through it. This symbol here shows a fuse. A fuse, remember, has a thin wire inside it, and that wire will melt if the current gets too high for the circuit, and that's a safety feature. We then have a voltmeter. A voltmeter is used to measure the potential difference. Remember that voltmeters should be connected in parallel to the device, so they go across it and out of the circuit. Beneath a voltmeter we have an ammeter. That measures the current, and ammeters, remember, should be connected in series, so they should be connected next to the component or device you want to measure the current going through. We now have 2 more resistors. The first one's a thermistor, which kind of got this hockey stick effect. Okay, and that shows a thermistor. Think of thermal. That's a thermal dependent resistor, so a heat dependent resistor. So for a thermistor, as your temperature increases, your resistance decreases. Beneath that we've got a light dependent resistor, an LDR, which is also called, and a light dependent resistor depends on the light it receives. And remember, as light intensity increases, the resistance of that component decreases. At the bottom there we've got an LED, or a light emitting diode. That works in the same way as a diode, except when a current goes through it in the forward direction, it will emit light and therefore will glow. Key thing to remember about the LED is that if the current goes in the reverse direction, you'll see no light and the current won't be allowed to flow because the resistance is so high. So diodes and LEDs only allow current to flow in one direction only. So the potential difference provided by cells connected in series is the sum of the potential difference of each cell, depending on which direction they are connected. So if they're connected correctly, as all these ones below are, then the overall potential difference provided by those cells is equal to the sum of all of those individual cells. So if we assume that each individual cell here has 3 volts, you'll be able to work out the total potential difference that each of these combinations have. So in the first combination we have 2 cells, each at 3 volts, so that's an overall combination of 3 plus 3, which gives us 6. The next combination of cells, we've got 4 cells there, they're all connected correctly, and therefore that will be 3 plus 3 plus 3 plus 3, or 3 times 4, which gives us 12 volts. The final combination here has 8 cells connected correctly, so that's going to give us 3 plus 3 8 times, or 3 times 8, which equals 24 volts. Now when we look at circuits, there's a difference between types of circuits. We've got series and parallel circuits, and each series circuit acts in the same way, and parallel circuits also act in the same way as other parallel circuits. So we're going to take series circuits first. There's two laws you need to know for series circuits, one for current and one for potential difference. Just a quick note to show you how the components such as ammeters and voltmeters are connected. You can see that the ammeters are connected in series, so that means they slot into the circuit, as shown in figure 1. Whereas in figure 2 we're seeing the voltmeter, and that's connected in parallel to the circuit, so it's connected across those components. The thing you need to know for a series circuit is that the current is the same everywhere. So you can see in the series circuit number 1, we've got 1 amp here, 1 amp there, 1 amp there. If I was to put an ammeter anywhere else, it would always read 1 amp because the current is the same everywhere. Remember, current is the rate of flow of charge, which basically means the number of electrons passing a fixed point in a given time period. So because the electrons have got nowhere else to go, the current is always going to be the same. Whereas the potential difference, the total potential difference of the supply, is shared between the two components. So if you imagine my electrons going into my cell here, they pick up 6 volts. They've got those 6 volts to go all the way around the circuit with. So if they drop off 4 volts here, that gives them 2 volts here. If you add those two things together, that gives you the 6 volts they got from the supply. So key thing to remember then for series circuits, current is the same everywhere, potential difference is shared between the components. So we move to look at parallel circuits now. Looking at parallel circuits, the total current through the whole circuit is the sum of the currents through the separate branches. So we can see at the top as we go past the cell, we get 3 amps worth of current, but when we get to this point here it splits, some goes this way and some goes that way. We have 2 amps going through the first branch and 1 amp going through the second branch, which if you add 2 amps to 1 amp, that gives us 3 amps, which is the total we get at the top. And at this point here, they recombine. So the total current through the whole circuit is the sum of the currents through separate branches. Whereas the potential difference across each branch is the same as that of the power supply. So if we start off here with a 6 volts going in, we'd have 6 volts here and 6 volts there, because it's always the same across a branch. Now if I was to add another component into one of these branches, then that one branch would behave like a series circuit, so the potential difference would then be shared across the components in that branch. But for a parallel circuit, you've got to remember the potential difference across a branch. I mean, a branch starts here and here, that's one branch. Here's the second branch between those 2 points. The potential difference is always the same. So just to summarise then, for parallel circuits, the total current through the whole circuit is the sum of the currents through the separate branches, and the potential difference across each branch is the same as that of the power supply. We're going to quickly look at current voltage graphs. So we've got the current voltage graph here for a resistor, and you can see that for a resistor you get a straight line on a current voltage graph. That's because resistors obey Ohm's law, so they obey the rule that V equals I times R, and R is constant for a fixed resistor, and therefore you get the potential difference equal to current, or proportional to the current, so we have a straight line that goes through the origin at 0, 0. For a bulb or a lamp, we don't get them to obey Ohm's law, so in this case we have a curved line. So the current will increase at a decreasing rate to a potential difference, and the reason for that is that at these points here, if you imagine before then we've got kind of a straight line going on, but afterwards we've got R increasing, and the reason that R is increasing in both those areas is that resistance will increase with temperature, and that increases with current. So remember that the current is determined by the number of electrons passing a fixed point at a given time period. As more electrons begin to flow, you have more collisions between the electrons and the ions, and as you get more collisions, the ions are basically going to heat up. As they heat up, they're going to move around more, and that's going to make even more collisions. So resistance increases with temperature. As the temperature increases, the ions inside that, which are basically the atoms that have lost electrons, are moving around more, and therefore there's more collisions between the ions and the electrons within the circuit, which increases the resistance. The final graph we're going to look at then is a diode, and a diode has the current increasing with potential difference in one direction but not in the other. So remember that for a diode, the current through a diode is in one direction only. The diode has a very high resistance in the opposite direction, which means that no current can flow. So here you can see that the diode will allow current to flow in this direction, potential difference, whereas in the opposite direction we get no reading at all on our ammeter. Remember that the graph for a diode is the same for a light emitting diode or an LED. LEDs emit light when current passes through them in the forward direction, and LEDs, it's important to remember that they use a much smaller current than other forms of lighting, which is why the use of LEDs is increasing. This last slide is just a reminder that you have an equation sheet in the exam. Remember that the equation sheet for the Unit 2 exams is two-sided, so you'll find equations on both sides of the equation sheet. So please remember to check the back. If you want to use the equation sheet, the best way to do that is to first of all find a term that's used in the question. So it might be that you're asked to work out power. So what you do is you look at the equation sheet and you'd find that power's there. You then write this equation, power equals energy over time, onto your exam paper, and then you would substitute in the numbers that you know. And then once those numbers have been substituted, you can then rearrange the equation to find the answer if you need to. Please remember to show all your working, and remember as well, if you're not given the unit at the end of the question, you need to include the unit, and the unit is always worth an extra mark. So even if you can't do the calculation, but you can remember the unit, so for example power is measured in watts, you can just write watts down at the end of the question, and that will get you at least 1 mark. Thank you for listening to this presentation. I hope you found it useful.